I suppose I'll just make any due dates clear before we start today's lecture. So the upcoming homework assignment is on measures of central tendency, which I did push back a day because I didn't finish everything last week. So measures of central tendency is now due tomorrow. So we'll finish it today. And if you have any questions, you could just, or need to schedule any office hours or anything, you can just shoot me an email. More than happy to help. Additionally, measures of dispersion, which we'll probably talk about that later on today. That's due on the 25th. See how far along we get with that. And the corresponding quiz is due Sunday. So in terms of the upcoming assignments for this coming week, those are the expectations moving forward. And besides for that, it's really all I have in terms of announcements. I guess I have to assign a workbook or something. I didn't even think about the workbook. Oh, we just don't do one. So everyone just want free points for the workbook. I don't feel like grading them. All right, that was easy. This Friday, do nothing. Just do absolutely nothing in terms of the workbook. Just get free points. You're welcome. So besides for that, any other questions? If you'd like to do the workbook assignments for the upcoming sections and you just want to do them in terms of feedback, happy to give you any feedback, just let me know. But besides for that, you don't have to do them. So sounds good? Cool. All right, that was easy. So let's go ahead and move on to where we left off. So we'll just kind of scroll up a little bit to just remind you that we've been talking about measures of central tendency. And so this is we started off talking about how to find these measures using the calculator, predominantly mean and the median. Mode is fairly intuitive to find. So we talked about finding the mean and the median by hand. Mean, of course, you add up all the values, divide by the total number. Median, put all the values in ascending order, find the middle one. And then we talked about how to do it on the calculator, which is insanely easy. So we've been talking about all of that. And then we also went ahead and introduced this idea of the 5-number summary. And the 5-number summary, well, as you would imagine, it's comprised of 5 numbers. Smallest number, first quartile. In fact, let me show the diagram while I'm at it. The smallest data value, the first quartile, the median, the third quartile, and the largest data value. And what these do is these values split the proportion of values into fourths. Kind of makes intuitive sense because we're talking about quartiles. Quartile, the prefix, referring to 4 something, so splitting it up into fourths. And we talked about some questions, or we answered some questions, for example, 10, about how these percentages work and how to interpret these changes from one 5-number summary value to another. And we're going to talk about that a little bit more upcoming. But one thing I wanted to mention was something called a box plot, which is a visual representation of the 5-number summary. And box plot, well, again, it's just visualization of the 5-number summary. That's it. So there's a number line down here, and above the number line are the corresponding numbers. So the lowest value that would correspond to that part of the number line. The first quartile would correspond to that part of the number line, and so on and so forth. It immediately drops down, and you could tell what the box represents. The box represents the quartiles as being the outer boundaries, and the median as being just this line in the middle. Well, it doesn't necessarily have to be perfectly in the middle. As we saw above, the distance, if it's oblong in any way, as in it's not symmetric, we might not get a bell-shaped distribution, as we talked about last time. But other than that, we'll be constructing a box plot here shortly, but wanted to give you an idea of how it's constructed. These little bits on the end are normally called whiskers, appropriately named. These little whiskers on the box. So, does anyone have any questions before we look at the next example? Is everyone all right? If not, example 11, and you already wrote this down or whatever, you might want to start typing those data values in. It takes a while. We're all going to do it. There are 46 values down there. You just pull out your calculators. We're all going to do this together. I'll make sure we get the right thing. You'll thank me later. How many points do teams score in the championship game of a certain sport? So here they just have a bunch of scores. And what we're going to do is take all 46 of these. Yes, this is a homework question, so that's why I'm making you all do it. And we're going to, we'll find the median, the quartiles, and answer various questions in terms of the defense and the 5-number summary and all this stuff. So we're all going to take those values and put that into the TI calculator. And it takes a while. And sometimes you end up typing it in incorrectly. So remember, you need some recollection. It is in the class notes as well. You have to press stat. And then from stat, you see edit. You press enter on edit. And it should bring you right to the screen, which hopefully you have L1 as a column. Just start typing in values. Type in the number, press enter. And we go from here. Give everybody a second to catch up. And one indication that you typed in everything correctly is on my computer screen here, it says L1 of 47 to imply that we've typed in 46 data values. So, and it should be 46 data values, so that should say 47. Sometimes people will miss one or add an extra one. But that's why I want to make sure everyone does this along with me. So from here, so once you have everything entered, and again, I may have typed in something wrong. I typed these in fairly quickly, but I might have typed in something wrong. We'll all apply the one variable statistics to this data set. So remember how that works. We have to quit out by pressing second in mode. From there, you click on stat yet again. Move your cursor over to calculate, or CALK, and there's one variable statistics. So we press enter, and no matter what calculator you have, just keep pressing enter until some numbers show up. Now, we can check each other, see if we all typed this in correctly, or if not, I might have typed it in wrong, so don't think what I have is inherently correct. So did anyone get the mean that I have? So, Chloe, what mean did you get?
It's the first one, right?
Mm-hmm.
Oh, 45.565317.
So say the first 4 digits, that the 40, 45.
5, 6,
sorry, 5.6. So 45.56. Who else got that? See, that's good. Mine's wrong. That's okay. So that happens all the time. So if mine is wrong, see, I typed mine in really quickly. So guess what I have to do? 46, 48, 23, 29, 29, 26. Oh, see right there, 57, that should be 47. Happens all the time. Oh, and I just deleted it. Fantastic. Oops. Forty, 42, 39, 47, 38, 55. Okay. That's right. Okay, let's try it. I'll just cheat and do that. There we go. Sounds good. I did, to quit out, you press second in mode. After you're done typing in the data set. And if you have the notes printed out, it says it, do you have the notes printed out by chance? It says it word for word on one of these pages here. Page 39, it gives you step by step. So as you can see, I typed in something wrong. Again, it happens all the time. This type of problem is common to show up on a test. So it's intentionally misleading because if you type in one thing wrong, guess what? Everything you type in is incorrect. So that's why I'm emphasizing this. But from there, we used the mean, even though we're not using the mean. That's a way for all of us to check ourselves. And let's figure out the median. With the median, just scroll down a little bit. Scroll down a little bit. And I got 46. I'm guessing everybody else got 46. Remember, the median is just MED. And they also tell us the quartiles. So notice the one variable statistics is a command that also gives us the quartiles. Q1, it says is 37. And Q3 says 55. The calculator gives us those directly. It's adjacent to the median value in the calculator. Now we can go ahead and find something called the upper fence and the lower fence. Now these are formulas I stated last time. We haven't used them yet. Let's go and remind ourselves of what these values are. You scroll up a little bit. The lower fence and the upper fence. Well, I have too much highlighter here. It's almost impossible to see. But this is where you can find them in your notes. So I'm going to rewrite them down here. So the lower fence, which I'll just call LF, and upper fence. The lower fence is Q1 minus 1.5 times IQR. Q3 plus 1.5 times IQR is the upper fence. Now, if anything, we know what Q1 and Q3 are. But what's this IQR thing? It's IQR. That's the interquartile range. So we have to figure that out right fast. In fact, I'll just put that perfect amount of space for it right up here in part B. The interquartile range, well, inter means, well, INTER means between, quartile, well, the quartiles, range, difference of. It's the difference of the quartiles. Q3 minus Q1. 55 minus 37, what's that about? 87, 57. Subtract 2, 18. Okay, so far so good. Now we found IQR. And we just plug in Q1 and Q3 into their respective parts in the formulas. Q1 we found to be 37 minus 1.5 times 18. The other one is 55 plus 1.5 times 18. (1.5 times 18 is 27, I believe, and 27 minus 37, that, subtracted from, that should be 10. Let's see if that's correct. 37 minus 1.5. Oh. 55 plus. It's 55 plus 27. 82, I think. Plus 5 times. So let's not mix up the order, because I did the lower fence first. So lower fence should go over here, next to its lower fence wording. 82 over here. That's it for the fences. Does anyone have any questions up to this point? If not, let's go ahead and fill in the 5-number summary in order. So the 5-number summary is always the minimum value, first quartile, the median, third quartile, and the maximum. Now the reason I wrote perhaps min X and max X is because for that 5-number summary, which means we're gonna, if you did anything with the calculator, you're gonna have to go calculate it again. Doesn't mean you have to type in the values again. You just have to go back to one variable stats and remember what some of those numbers were. It tells you everything in order. Min X, oops. Min X is 21. We already know the first quartile. We know the median. We know the third quartile. And the maximum's 75. The calculator gives us the 5-number summary in order. It's very convenient. So everyone good up to this point? So we're going to construct a box plot of the 5-number summary. So the way we always start this is, well, we start with the minimum value, or we can start with the minimum value. That's 21. Minimum value is, of course, 21. There's a 20 on our number line, so right above that, I'm going to put a line slightly past 20 to just resemble 21. All right, there's the minimum right there. All right, then I'm going to draw another line for wherever Q1's at, which is 37. With 37, I see 30, I see 40. It'll be closer to 40. I'll put it right about there. And that'll be Q1. And what I'm going to do is draw a little line connecting them two.
Yeah, man, how you put it right.
No, that shouldn't matter. I mean, on the homework, it'll be multiple choice. So you won't even have to construct these by hand, especially because I just said you don't have to do the workbook assignment for this week. Okay, so there's Q1. So we drew the leftmost whisker. All right, the median, we do the same thing. Median's 46. There's 40, there's 50, maybe a little bit more than halfway. And before I connect anything here, I'm also going to draw in Q3, which is 55. Go ahead and do 55, which would be directly halfway between 50 and 60. Now this is where the box comes into play. In the box plot, it needs a box, right? That is the box. Oh yeah, that's Q3 on that end. And then finally, we need to draw a line where 75 is at for the maximum, which will be, of course, between 70 and 80. And this will also be a whisker. And so we just drew a box plot. And this gives us an idea about the spread of information. In fact, these sorts of models are used a lot in stocks. If you go and check out the the candle box diagram for any stock, I mean, you could see stuff move up and down, but you can view stocks in another way. And they'll show the candle box version where they'll show these diagrams just rotated 90 degrees. It's another interesting way in which any sort of financial advisors or any other people invested in the stock market like to see relations among trends of various stock prices. And something about volume, but I don't know stocks that much. Okay, box plot, pretty straightforward, or no. And then there's one more part. And this problem is sometimes a bit misleading, so let's tread through it carefully. So teams typically score a total about blank points. Does anyone have any intuition what goes into that blank?
What did you say?
What did you say?
I said
The median? So the word typically sometimes evokes the mean, but we're not dealing with the mean in this problem. They only want us to look at the 5-number summary. So we're going to go with the median. We're on the assumption that we're trusting the median here. So this will be the median, which, what did I say the median was? 46. So the median. Because remember, the median is a measure of central tendency. So it's a measure of expectation. With half of the games totaling more than blank, but less than blank points. What about those two? Well, that would be, so this one's just half. From the min to the maximum, that would be not half, but everything. We want just half. Just half. So what about those two blanks? Yeah, this one, well, this one's going to be the first quartile and the third quartile. There's a reason why I'll explain here momentarily. So more than the first quartile and less than the third quartile. I want to scroll up right fast. Here's the first quartile. Here's the third quartile. Going from one to the other elicits how or what percentage of data values? 25%, 25%, 50%. That's the middle 50% right there. The middle 50% of the data lies within the quartiles. And that's just always true. That's just true in general. Okay. In only 1/4 of the games have the team scored fewer than blank points. What about that one? 1/4, that's 25%, fewer than blank points. So nothing smaller than the minimum. So 0% would be smaller than the minimum. You're gonna have to go larger than the minimum. Because from that value, there has to be exactly 25% less than that value. It's going to be 37 again. This problem's kind of misleading because people will see the 5 blanks and think each 5-number summary goes in like a word bank. But this is the first quartile again. So 1/4 fewer than, if we go back up to that diagram, so I'm going to detour right fast. So we were at the first quartile. What's fewer than the first quartile? So that goes all the way from here to this value here. And that's 25% of the data. If we started at the smallest data value, there's no smallest one to jump to. So that would be 0%. If it were from the median, that would be 50%. If it were from Q3, fewer than that is 75%. That's kind of how we read this chart. It gives us an idea about the intervals of 25%, the proportions for which the amount of data lies within certain intervals. And the most the teams ever totaled was 75. Yeah, so that we finally get to use one of those min-max values because it's saying the most. So what's the most? The max. Okay, so that concludes that problem. Does anyone have any questions up to this point? So if not, that does conclude this section. And with this section comes the corresponding homework, which is due tomorrow. So again, if you have any questions about this homework, email me before 8 p.m., please. Either tonight or tomorrow night. Or if you need office hours, email me. We can arrange that. Besides for that, let's go ahead and move on to the next section. So we're moving on to the section on measures of dispersion. Now, the terminology here, at least some of the terminology might be familiar, but we're also going to be introducing another idea that may not be as familiar as the mean, median, and mode was from our perhaps elementary, high school education, whenever they teach that stuff. Workbook assignment, none. I'm just going to give you the free points. So none, don't touch it. If you just walked in late, I'm not doing any workbooks this week, get the free points. Doesn't matter. So none. So let's start talking about the measures of dispersion. Measures of dispersion. So let's sort of set up the scene a little bit. There's two classes. One class has a mean of 75%. Oh, and kind of interesting, the other class also has a mean of 75%. So are these classes performing at the same, actually, let's make this even more simplistic. Two classes performing at 50%. Just say it's just a really bad class. One class is an average of 50%, the other class is an average of 50%. Are these two classes performing at the same level? Is one class doing better than the other, or can you conclusively say that these classes are operating at the same level? They're both doing as well as each other.
As a whole, I feel like it would be the same level, but then you might have like one student, one class with a higher one than the other class.
Yeah, so let's kind of spice this up a little bit. So one class, let's just say for one class, say this class is 40 students. 20 of the students have 100s, and 20 of the students have zeros. Well, that sounds, I know it sounds ridiculous, but this is a math class. There's a lot of ridiculous word problems and stuff. So, but that would elicit an average of 50%. So 20% or 20 students with 100%, 20 students with 0%. And then there's another class where there's 20 students with 60% and 20 students with 40%. But they both elicit the same average of 100%. So it turns out, so these two classes are performing differently. Now, how you want to define better in terms of some sort of partial ordering is perhaps a philosophical question for another class. But ultimately, this idea of just viewing a data set based off of the center is inconclusive, because not only is there a center, but the center is not the only thing going on. What about the stuff going on around the center? The stuff going on around the center, how do we measure that stuff going on? Well, these data values are measured by how much they are dispersed from the mean. And this measure of dispersion is the motivation for why we not only look at the center, but how close the data is around the center. And that's when we move on to the measures of dispersion. Now, one of these measures should be very familiar. It's the range. The range should be the familiar one. It's the difference between the maximum and the minimum. It tells you, all right, here's the largest value, here's the smallest value. What is the distance of that interval? That's what it tells you. Distance between the maximum and the minimum. The range is a very quick measure for determining the dispersion because it tells you how large is the interval for which the data values spread. But however, the range is not a good measure because all it does is take two values into consideration, the maximum and the minimum. It doesn't take every single data value into consideration. And we might want to know what those values are. There might be two outliers on the very far ends, and then all the other data is very squished together. That would be a very misleading picture. So instead, what we care about is the standard deviation. That is the essence of this section, the standard deviation. And this is a qualitative approach for determining or measuring how much the data spreads from the mean. So the standard deviation describes how much the data varies from the mean. So you're going to get one number out of this, and this number will somehow tell you what to expect in terms of dispersion from the mean. The smaller your standard deviation is, the closer the values are to the mean. This normally corresponds to more consistent data. You have a center, and then you have values really close to the center, then you're getting consistent data. Now, if you have a very large standard deviation, then that means your data is sporadic. It's a bit out of control. So generally, the best example used is grades in a class. Now, normally 99% of classes, they have the center is some grade in some C grade, and then there's a lot of grades that are within the B to D range around that average, and then with less A's and F's. Well, that's normally the expectation. And so the equation we're going to be using is the simple formula right here. No, I'm just kidding. We don't use this formula in this class. We definitely use the calculator. We will never touch that formula. If you take me for stats or anyone for stats next semester, you will also not touch this formula unless your teacher is maniacal. But generally, the TI calculator does all of this for you fairly quickly. And so the resolution of all of this is that the range is a quick but rough measure of dispersion. It's very quick because it's just the difference between two values. The standard deviation, which I normally notated as STDEV, or sometimes a lowercase s. There's a few different symbolisms for it. Sometimes we use lowercase sigma, which you'll find out more about that if you take statistics next semester. But with all of this being said, it's just a fancy way of concluding with this is stuff that the calculator gives us, and we just need to know how to interpret it. Now, we'll start off with a very simple scenario. Given a mean of 62, a standard deviation of 1, again, you don't have to know what that 1 means for now, they're just telling you that. Construct a graph that represents all the data within 2 standard deviations of the mean. Okay, that might sound weird at first because we're just talking about the standard deviation. If anything, let's start with something concrete, the mean. The mean is 62. There's 62. Okay, so far so good, that's the mean. Now, let me toss this question up to you all. What value would be, all right, so listen to me closely. What value would be 2 standard deviations above the mean? 64. It'd be 64. Now, where did that number come from? 64. That would be 2 above. Now, 62 is the mean. If we want 1 standard deviation above the mean, just add 1. We asked for 2. So you're technically adding 1 again. And I'm going to get into this in more detail later on, but that would be above the mean. And this is pretty symmetric. So below the mean, well, instead of 64, 2 below would be 60. And that would just be 62, but since it's below, then we would subtract not 1 standard deviation, but 2 standard deviations. That's where we get 60. And so this is the answer. Simple as that.
So 60 and 64.
60 and 64 are the 2 values below and above, respectively. But for this problem, it's going to be a multiple choice, I believe. And you just select the one where 60 and 64, whatever your equivalent numbers would suggest. Okay, let's look at another situation. The median selling price of new homes in a state in 2002 was $145,500. Okay, so they're telling us the median, which is some measure of central tendency. Which of the following is the most plausible value for the standard deviation? All right, so now we're thinking, okay, so we barely know anything about this, but now you're wanting me to interpret this. Yes, I am. And so let's, my spacing's kind of off here. I don't know why. These are all separate values. I don't know why they just randomly spaced after some of the commas, but those are the 4 values that we are tossing up for the standard deviation. So any one of those 4 values are being supposed as the standard deviation. And so the question is, well, which value or values would not be plausible? So we can pick one via process of elimination. So the standard deviation explains the spread from the mean. And when I say this, 1 standard deviation away from the mean should give us an interval, because 1, let's see, above from your perspective would be this way. No, yeah, I don't know, this way. I don't know. The mean being in the center, we want a standard deviation above and below. So that gives us an interval. This should be a very expectant interval. So if anything, there's one of these values that we can knock off immediately. Standard deviation can't be negative. So that was pretty easy. In fact, I asked this question last semester. I can't give bonus points in this class, but I definitely would if I could. Why, using the formula above right here, why can the standard deviation not be negative? Not that. You can have negatives in the denominator.
It'll be imaginary numbers because it's in the square.
So this is saying that s of x would be the negative 18. So it won't, the negative is not in the square roots, but it does have something to do with the square roots.
Yeah, negative.
The output of a square root can never be negative. If you take college algebra, you'll have to know that, but I figured, that was a pretty interesting problem to ask. Yeah, you can't output a negative with a square root. But if that negative was in the square root and it came out as such, I don't know. That's kind of food for thought. All right, so that leaves us with 3 other standard deviations. So let's look at 1 million as a standard deviation. So it's saying that the expected values of homes will fall within a standard deviation of 1 million. So let's just explore what the repercussions of that are. So if we looked at 1 standard deviation below the mean, or the median in this case, and then 1 above, there's going to be some crazy numbers. Oops, that should be an extra 1. 1, 4, 5, 5, 0, 0. So it's saying that homes would be generally expected to fall anywhere from negative $854,000 about to $1.15 million. Sounds a little outrageous for expected homes, typical homes. So, you know, homes that we would all reasonably perhaps live in. So $1 million just seems way too large in terms of showing us the fair diversity of expectant home values. So let's get that up. So that leaves us with 50,000 or 7,000. Minus 7,000 plus 7,000. That'd be for one of them. And then 50,000 on the other hand. So let's think about the repercussions of some of these values. 145,500 minus 7,000. That would be plus sign 152,500 minus 50,000. And we have one more. And then we can go ahead and interpret all of this. $95500. Okay, so with these spreads, a standard deviation of 7,000 means that we can generally expect homes to be around 138 to 152,000. Now, on the other hand, a standard deviation of 50,000 tells us we can expect homes to be anywhere from 95,000 to 195,000. Which one seems more typical? This is in a state. So the 7,000, I'm going to argue, now this might be an unfair problem for people who might not be aware of the housing market, especially in 2002 when probably some of you might have been born, but there's a fairly decent variety in terms of the values of homes, a lot more than this very limited interval from here to here. There's definitely homes that are much lower than 138,000. How nice are they? That's relative, but there are a number of homes that explore a lot more diverse of a range. And this one over here, the 50,000, gives a lot more realistic idea of the diversity of homes, especially in a state. Think about it. States have rural areas, urban areas. Rural areas would have a tendency, or maybe even various spots in various cities that may have homes that may not be as expensive, and there might be affluent areas in a state that may bring up the property values. But to express this diversity as a number, 50,000 does a lot more reasonable of a job to explain this. So we're going to go with 50,000 here. 7,000 is just way too. What's that?
I think the 7,000 for a house is like too little of a range.
It's too little. It's.
I feel like that would be better for like a car or like something like smaller that you were buying, maybe.
A car, yes, because car values also are smaller, which means that their values that they could spread are additionally much smaller. In fact, if any of you ever use Kelley Blue Book, this does offer I was going to talk about this example, I think, next time in class, but Kelley Blue Book, you're looking at prices of a car. It gives you a somewhat bell graph of expected values, and that it does give you, in a sense, it's based off of the standard deviation. Kind of interesting stuff. Yeah, a car would be more reasonable for 7,000. That is definitely true. And then maybe for those fancy pants millionaires, maybe the million might be more understood for them. All right, let's move on to example 3. Let's figure out how to find the standard deviation in the calculator. You will never have to do this by hand. It is a horrible process. Any teacher that makes you do that, you should complain immediately. So we're going to figure out how to do all this in the calculator. Now it turns out we already know how to do it in the calculator because it's the same process for finding the mean and the median and all those. Standard deviation's been there the whole time. We've just been ignoring it. So let's go to stat. We're going to go to edit because we need to edit in the data set. And right where L1 is at, if you want to clear out the old list, you move your cursor up to the name of the list. So just like that, up to the name of the list. And you press clear and enter. And it clears it for you. Now you don't have to delete 46 different entries. Cursor up to name of list, press clear and enter. That's it. And you should have a clean slate. And from there, let's go ahead and type in these values. Don't forget about the decimal. 0.58 and 0.74. And let's do all this for now. And once you have all that typed in, second in mode to quit out of it. So back to the main screen. Click on stat again, over to CALC, enter, enter. I might have the right answer, I might not. Type it in. Did you get the same mean that I got? You're saying yes, yes, yes. So I'm trusting what I have is right by the power of majority.
Is it 12?
What's that?
Is it 12?
12 for,
The answer to the very top of about.
so the, well, if you got 12 for the bottom one, for the top one, did you get 3.89 and a bunch of sixes? All right, you typed it in perfectly. All right, cool. That's just a good way for us to reassure that you typed it in right, I typed it in right. And from here, remember the mean, and I'll just type in the X bar just to remind you all. That's what the mean is. It's the very top number. That's what they're asking for first, rounded to 2 decimal places. So that's 3.90 when we round. This is a 6, rounds to 9, to a 10, you carry the 1, that's 9. So, but now they want the range. I'm looking on here, I don't see the range. Well, what did we do? Did we do something wrong? Not really. The range is easy to find.
Just find the biggest.
I mean, they already tell us the max and the min in the calculator. So it's, they tell us the max is 8.15 minus the minimum, which is 0.58. And that's it. Whatever that difference is, 8.15 minus 0.58. 7.57. So we don't really need the range, but they tell us the max and the min, which we can figure out the range very quickly. And of course, I already exited out. So let's go back to the 5-number summary. And if you scroll down, actually, you don't even need to scroll down. The standard deviation, this is our first time looking at this, is the value that says SX. SX in the calculator. And to 2 decimal places, that's 2.90. So if it helps, standard deviation starts with an S. It's an S. Just make sure you choose the right one. Okay, so that's that problem. So that's just a very quick way of seeing how to figure out the standard deviation in the calculator. Does anyone have any questions before we look at the next example? Okay, let's move on to example 4. So this one's a lot easier to type in the calculator. They want us to figure out the mean and the standard deviation of this piddly little set of values right here. So let's go ahead and do that. Go back to stat and edit, so we can edit in the values. Move the cursor up to L1, press clear and enter. Start over. And we can go ahead and type out those 5 values. Quit out of that, go to stat, calc, and variable stats, and should be good. Did I lose anybody on that process?
And it's the same as just add all of them up and divide by 5.
Well, for the mean, but we'll also need the standard deviation. So we definitely need to do this process for the standard deviation's sake. Because as we saw above, that formula looks horrendous. So hopefully you obtained a mean of 7 and a standard deviation of 2.74. And if you did, that means we all typed it in together correctly. If you did not, maybe I typed it in wrong, maybe you typed it in wrong. So I haven't heard any objections, so I'm assuming everything here is good. So the mean is 7. The standard deviation, they want it to the nearest hundredth, which is 2 decimal places. 2.74. So far, so good. Pretty simple. Not so simple. Next part, it says multiply each number by 2. Okay, so the numbers in our data set, they want us to multiply each number by 2. Okay, so 3 times 2 is 6. 6 times 2 is 12. 9 times 2 is 18. 20, and 14. And then they tell us to start over. Okay, so let's clear this out, go back to our data set, and then just put in the new values. We're basically saying just do this, but with the new data set. And so we get 14 for the mean, and a standard deviation of 5.408 to the nearest 100. Okay. Now it wants us to multiply all of them by 4. We're thinking, okay, this is a fairly tedious process. 3 times 4 is 12. 6 times 4, 24. 9 times 4 is 36. And 40, and 28. So let's do this one more time. 12, 24, 36, 40, 28. And so one more time, we get a mean of 28 and a standard deviation of 10.95. Now, question. Does anyone happen to notice a pattern here?
Means the last number.
What's that?
The means the last number. And the row.
Well, maybe let's, well, okay, well, that is a pattern, so I can't deny on that. That is a pattern. How about comparing the means in each situation? So those two means. What's that?
It's just nothing.
You're doubling it. And then what about, let's try from that mean up here to like 28. Really quadrupling it. But notice what we did, multiplied by 2, multiplied by 4. So that's not really a coincidence. In fact, that should happen. If you multiply your data set by 2, you're going to multiply your mean by 2. If you multiply your data set by 4, you're going to multiply your mean by 4. What about the standard deviation? It's 2.74 times 2, 5.48. That's interesting. It's 2.74 times 4, 10.96, which we rounded a bit, so. But it's the same for the standard deviation. So basically, if you multiply your data set by a number, generally that's called a scalar because you're scaling. If you multiply your data set by a number, your mean and standard deviation will get multiplied by that same number. And so that helps with part D because they do give you a data set, which you don't even have to type into the calculator. Because they tell you that the mean is 5 and the standard deviation is 2. And then they tell you, well, the mean's 5, standard deviation's 2. What's the mean and standard deviation of that data set? Yeah, you double. You just double everything. Because notice the 2 becomes a 4. 4 becomes 8. 5, 10. 5, 10. You're doubling everything. So guess what? You double the mean. So 5 times 2 is 10. You double the standard deviation. 2 times 2 is 4. That's it. And we're done with that. Does anyone have any questions before we move on to the next example? If not, let's look at example 5. All right, these are kind of annoying problems because you have to interpolate a little bit. Interpolation, I'll kind of explain what I mean by that momentarily. Basically, you kind of have to estimate some stuff in between values. Okay, so there's a chart for height, there's a chart for weight. The black line represents the mean values. So of course it makes sense that as people get older, their height increases. And then you just kind of stop growing. You just stop growing at some point. And same thing with the weight. And this is measured up to, I believe, 18-year-olds. So as you get older, you start to weigh more because of course your body grows into maturity. So these are measured, and so the first thing they want us to do, so what happens to the, before I start the problem, the blue shaded part, so if the black line's the mean, the blue shaded part represents 2 standard deviations from the mean, both below, so below would be down, and up. That's what the blue shaded region is. It's 2 standard deviations from the mean. And these would be considered the normal range of values. So these would be the normal range of values. And so let's kind of interpret that with these upcoming examples here. They first ask, what happens to the standard deviation, so the blue shaded part, or teal, I'm not good with colors, whatever color that is. What happens to the standard deviation for the weights? So the weights tell us, let's look over here, as the age increases. Does the standard deviation grow or does it shrink? It grows. As the age in years increases, Notice the shaded part gets a little bit wider. It's a little bit wider. That means, you know, as babies, we don't really have too much diversity of weight. We come out, was it 8 pounds? Isn't that average? 7 pounds? As you can tell, I'm not a father. I don't know, but something like that. There's not too much diversity. And then as people get older, of course, weights and similarly heights start to become diverse as we start to mature into our bodies, genetics, all the other factors of life. So this increases, Or in other words, there is a greater spread, as in there's more diversity as we get older. I feel like with parents, they always seem to know the exact weight their child was when they were born. And I don't know, I guess I could look at the chart and find out, but oh well. Okay, so that's more interpretive, to say the least. So let's move on to part B, which is a little bit more specific. Okay, so we're back onto the weights at age 16. So the weights and at age 16. So age 16, you're looking right there on the chart. So pretty much this column of values to give some sort of specific aid to this. The mean weight is blank. So basically, so remember the mean weight was that black line. So basically it's asking if we go up at 16, where's that value at? And it might be hard to see if you're in class right now, maybe if you're virtual as well. It'll be a little bit more clear when you do the homework, but it's in between two grid lines. So you kind of have to interpolate, which means you have to kind of guess. So let's see, if we go over here, that's about 130. So that's 140, 130. From my perspective, I would say that looks like 100 and, so let's yes, that was 130, 132. They'll give you a good margin of error. Looks like 132 to me. Again, you can give it 131, I think up to 134, 135. That's kind of where it looks like though. It's less than half. So less than 135, but that's kind of the annoying aspect about this. This is the only reason why I picked this problem. It's because these little tidbits of interpolation get a little bit tedious. Okay, so let's move on. And the reference, that was the point which we were looking at. Okay, so part C, the approximate standard deviation at age 16. So we're back looking at the same part right here, but now they want to know about the standard deviation. They want to know about the spread now, not the mean. They want to know about the distance from the mean. So I'll use blue. So this would be the distance from the mean to one of the boundaries of the standard deviation. So this in blue, that would be referring to how the mean and the standard deviation relate. Now, if we were to look at this distance, now the good news is at least, okay, it's not good news. It still falls underneath the grid line. So we need to figure out a way to find that difference. Again, we're going to have to kind of guess at it. So basically, what is this distance from the black line to either the part above to where the shaded region ends, or you can do it below. It doesn't matter. They're going to be the same. It's two standard deviations nonetheless. Now, if we said the bottom one was 132, the top one, so it seems seems to be right there. So it's fairly close to what seems to be 170. Say 168. Again, might be 169, might be 167. Looks like 168 to me. So this one we already said was 132. The difference between those two is the connection cutting out for anybody else virtually? So just let me know. For those of you virtual, I could send the recorded lecture if you would like. I haven't had that happen before, so I'm not too sure how to. Oh, okay, it's better than cool. Offer still stands. If you missed anything because the connection messed up, just let me know. Okay, so 168 minus. Oh, you have a question?
How come you didn't do the top shaded part and the very bottom shaded part? Like, didn't want
Because we want to know the difference from the, because when we look at standard deviation, it's standard deviation from the mean. And so we have to involve the mean as part of the difference, because standard deviation doesn't mean anything unless we have the mean involved as well. So that's why we have to include the mean in there. And so that difference, 40, 50, 60, so that is 36, it seems like, but that is not the answer, which is why I'm writing it off to the side here. Does anyone happen to see what the answer is? I'll kind of scroll above to maybe show a little bit of a hint in how the problem is described.
to go over to height?
So not over the height. What we actually found was
The mean of two standard.
we found two standard deviations. So very sneaky. They just want one standard deviation.
They just divide it up.
You divide it by 2, that's right. So really what they want is 18, because the shaded part represents 2 standard deviations. Yeah, so that's, again, there's a lot of reasons why I'm picking this problem. A lot of tricky stuff going on here. This is really 2 standard deviations. So that means you have to divide it in half to just get 1 standard deviation of 18. Okay, so let's move on to part B now. Now they want the mean weight and the normal range for boys at age 15. So on our graph, let's clean this up a little bit, because now we're looking at 15. They want the mean weight. Weight means we're still looking at this graph off to the right. And so the mean weight is simply, where does that black line cross at? Now, again, it might be a little bit hard to see on my end, but it's slightly above. It almost looks like it's on 120, but it seems like it's the slightest bit above. If you haven't printed out, it might or might not seem clear like that. I'd say it's 121 though. Again, it's sort of tough to see. On my end, it looks slightly above the grid line. So that would be, in my opinion, 121. Again, if you put 120 or 122, I'm pretty sure it'll accept it the same. So what's the mean? 121. And then the normal range. So now the range is implying that they want the lower value and the upper value. Lower value being down here, upper value being up here. They want those 2 values. And I would imagine in order. So let's try to figure that out. The lower value right here. So they want this value. That seems to be above 90. Halfway between 90 and 100. It seems to be 95 to me for the lower one. The higher one seems to be a little bit above 150. Let's say 152. That's what it looks like to me. A little bit above 150 because these go by increments of 10. They only just show or label every 20. Okay. Let's go from there. So now we're going over to heights. So now we look at the mean height and normal range. So we look at a whole new graph. Hopefully we get some more exact values at age 15. So same thing, different chart. Height, age 15. So bad news is we still have to interpolate. At 15, this, in fact, I'll put it in blue to emphasize it. That seems to be, well, our increments are a little bit different. This is between 65 and 70. So I'd say that's 68. I'd say that's comfortably 68 for the mean. And then for the normal range, as they call it, so that seems to be in between 60 and 65. Say that's 63. And then this last one between 70 and 75 looks like 74. Again, it's just, they give you a few units of a margin of error, 63 and 74 though. Okay. Does anyone have any questions up to this point? If approximately 95% of all boys are in the normal range, what percent are not in the normal range? 5%. If 95 is normal, what percent is not normal? 5%, the remaining 5%. I'm calling it a day here. I'm tired of looking at these graphs. So I'll wrap it up here. Homework for this is due, or not for this, but for the central tendency, that's due tomorrow. If you have any questions, need to talk to me about anything, let me know. Other than that, have a good day.